Welcome back, everyone. Today, we're diving into one of the most intriguing discoveries from space in recent months. Scientists working with the James Webb Space Telescope have uncovered surprising new details about Mercury, our smallest and hottest planetary neighbor. Known for its extreme temperatures and proximity to the Sun, Mercury might not seem like the place for groundbreaking findings, but Webb's latest data is proving otherwise. From unexpected surface characteristics to atmospheric mysteries, Mercury's secrets are now being revealed like never before. Stick around as we explore these 5 fascinating revelations. The James Webb Telescope's advanced infrared capabilities have allowed scientists to analyze Mercury's surface composition more deeply than ever. Surprisingly, Webb's data suggests that Mercury's surface is rich in certain elements like sulfur, more than scientists previously thought. This raises questions about the planet's formation and evolution, as sulfur is generally less abundant in rocky planets. Since Mercury lacks an atmosphere to protect it, surface elements typically change under intense solar radiation, yet Webb's data hints at an unusual resistance to this process. Could Mercury have a hidden history that's yet to be unraveled? Another shocking discovery made by the James Webb Telescope is Mercury's magnetic field behavior. While we've known Mercury has a magnetic field, Webb's data has revealed fluctuations that defy standard models of planetary magnetism. Unlike Earth's stable magnetic field, Mercury's field appears to change in response to solar activity, which could be due to its small, rapidly cooling core. This discovery gives scientists new insights into planetary magnetism and how a planet so close to the Sun can maintain any magnetic field at all. What secrets could this hold for understanding the evolution of magnetic fields on other planets? One of the most exciting revelations from Webb's data lies in Mercury's exosphere, a super thin layer of gases instead of a full atmosphere. Webb has detected variations in elements like sodium and potassium within this exosphere. These elements appear in larger concentrations than expected, suggesting that Mercury's proximity to the Sun could be causing a unique kind of space weathering. This finding hints that Mercury might experience frequent chemical reactions on its surface due to solar radiation, which contributes to this intriguing exosphere composition. Could these reactions impact Mercury's surface over time? Mercury's temperature has always been extreme, ranging from 800 F during the day to 330 F at night. However, Webb's observations have shown that these temperature shifts are not as uniform as previously believed. In certain regions, temperature changes seem less drastic, which could suggest the presence of material insulating the surface or an unknown thermal regulation process. Understanding these variations could reshape our understanding of how planets without atmospheres interact with solar energy. If Mercury can maintain such irregular thermal characteristics, what could this imply about planetary resilience? Yes, you heard that right. Scientists now think there could be traces of ice on Mercury. Despite being the hottest planet in our solar system, Mercury has deep craters near its poles that are permanently shadowed, where temperatures remain cold enough to trap ice. The James Webb Telescope has picked up signals that may confirm this long-held theory, providing crucial insights into how ice can exist even in such extreme environments. This discovery raises questions about water delivery in the inner solar system and whether other planets, like Mars, might have hidden water reserves in unexpected places. Data from the James Webb Telescope has revealed that Mercury's surface might have more mineral diversity than previously thought. Scientists had initially believed that Mercury's close proximity to the Sun and its lack of an atmosphere would limit its mineral variation. However, Webb's data indicates a complex variety of minerals across the planet's surface, with unique rock formations unlike those seen on Earth or other rocky planets. These minerals may reveal more about Mercury's volcanic history and the intense geological processes that shaped it over time. One of the biggest surprises in recent data is how unusual Mercury's core appears. The planet's core makes up a much larger portion of its mass than other terrestrial planets, and Webb's observations suggest it might be partially molten despite Mercury's age. This discovery raises questions about why Mercury's core has stayed warm for so long. It could be due to unknown radioactive elements or leftover heat from planetary formation. Unlocking the secrets of Mercury's core could reveal clues about planetary formation across the solar system. The James Webb Telescope's findings point to signs of ancient volcanic activity on Mercury, with possible lava plains across its surface. Although Mercury has been geologically inactive for billions of years, these remnants hint at a time when Mercury was more volatile. Ancient volcanic activity might have played a role in creating Mercury's current landscape and could provide insight into the intense planetary cooling that followed. Learning more about Mercury's volcanic past might help scientists understand how planetary bodies age and change over time. Webb's high-resolution images have captured more details about Mercury's tectonic features, including strange, large scarps or cliffs. These tectonic scars suggest Mercury has shrunk slightly over billions of years as it cooled, leading to the formation of large faults and cliffs on its surface. Studying these tectonic scars provides insight into how planetary crusts can contract and reshape a planet's surface. This could also shed light on how other rocky bodies in the solar system evolve over time. Mercury's surface rocks are continuously bombarded by solar radiation due to its proximity to the Sun and lack of atmosphere. Yet, Webb's data shows that certain rocks on Mercury's surface have an unusually high tolerance to radiation. These rocks seem to reflect light differently than others, likely due to specific mineral properties. Understanding these radiation-resistant rocks could inform scientists on how to develop materials that can withstand extreme environments, perhaps even for use in future space missions. In a twist, Webb's data suggests Mercury's magnetic field may have reversed in the distant past, flipping its magnetic poles. This reversal is puzzling, as Mercury's weak magnetic field doesn't behave like Earth's, which undergoes regular reversals. Studying this reversal could reveal patterns that tell us more about Mercury's early core dynamics and provide clues on how magnetic fields are sustained, even in planets that are small and close to the Sun. Mercury is constantly exposed to the solar wind, which bombards its surface with high-energy particles. Webb's observations suggest that these solar winds have stripped away materials from Mercury's surface over millions of years, causing a slow but steady erosion. This continuous erosion might explain some of Mercury's surface features, such as hollows, which are shallow depressions. The study of solar wind erosion on Mercury could help scientists understand how solar activity affects planets without atmospheres. James Webb's data has revealed that Mercury's environment is a hotspot for space weather events with high solar particle activity. These conditions cause significant stress on Mercury's surface, altering its chemical composition and even affecting its exosphere. By studying Mercury as a model for intense space weather, scientists could learn how solar storms and radiation impact planets throughout the solar system, especially those closer to their stars. One of the peculiarities of Mercury is its unusual orbit, where it precesses or shifts slowly over time due to the Sun's gravitational pull. Webb's recent data on Mercury's position and movement around the Sun could provide the most precise measurements yet of this phenomenon. Studying Mercury's precession helps scientists test predictions of Einstein's general theory of relativity and understand how planetary orbits are influenced by gravitational forces. Webb's observations have detected volatile elements, such as potassium, in Mercury's surface material. The presence of these elements is unusual for a planet so close to the Sun, where intense heat would typically cause them to evaporate. This finding suggests that Mercury may have a unique ability to trap or retain certain elements despite its high temperatures. Investigating these volatiles could uncover clues about Mercury's composition and even the history of material distribution in the inner solar system. One of the more unexpected findings from Webb's data is evidence that Mercury's thin exosphere may contain tiny clouds of sulfur. Although Mercury doesn't have weather as we know it, these sulfur particles are likely ejected from the surface and briefly suspended in the exosphere. Scientists are interested in studying these clouds to understand how extreme solar radiation affects Mercury's surface materials and to investigate any parallels with the formation of atmospheres on other planets. Webb's data hints at the possibility of ancient water traces on Mercury, detected as faint signatures in some of its rocks. These traces might suggest that Mercury was exposed to water-rich asteroids or comets in its distant past. If true, this could reshape our understanding of how water, a critical component for life, was distributed across the solar system billions of years ago, even on planets as hot and hostile as Mercury. Webb's telescope has detected unique silicate rock types on Mercury's surface, indicating a more complex mineralogy than previously assumed. These silicates, which likely formed under extreme heat, could reveal valuable information about the planet's early geological processes. Examining Mercury's silicate rocks could provide insights into the high-temperature processes that shaped the inner planets and potentially even explain the origins of some terrestrial minerals. Despite Mercury's core being predominantly iron, Webb's data has found only minimal iron presence on the surface. This finding is puzzling because it contradicts what scientists expected based on Mercury's high density. The absence of iron suggests that intense solar radiation or volcanic processes may have altered Mercury's surface composition. Understanding this discrepancy could clarify the role of the Sun in shaping planetary surfaces and reveal how Mercury's evolution differs from other terrestrial planets. Finally, the wealth of data from the James Webb Telescope has reinvigorated interest in Mercury exploration. With so many unanswered questions, scientists are considering potential future missions. Unique exosphere could provide insights essential to understanding rocky planets, including Earth. Mercury, once thought to be a simple and predictable planet, is proving to be anything but, and scientists are just beginning to scratch the surface. Mercury's field sometimes temporarily aligning with solar winds. This phenomenon, known as magnetic reconnection, may cause fluctuations in Mercury's magnetosphere and even affect the surface. Studying this further could reveal how planets close to their stars manage magnetic forces, a topic of interest for understanding exoplanets as well. One of the more speculative findings from Webb is the possibility of a faint, thin ring of particles around Mercury. This ring, if it exists, could be composed of particles ejected by solar wind impacts or remnants of micrometeoroid collisions. Unlike Saturn's rings, Mercury's would be incredibly faint and temporary. Investigating these potential rings could provide clues about Mercury's interactions with the space environment and the effects of its lack of a strong gravitational field. Webb's data has shown that solar radiation on Mercury affects surface elements in unusual ways, causing some to sublimate or evaporate and then redeposit across the planet's surface. This redistribution process could create localized deposits of certain minerals, resulting in unique surface patterns. This discovery helps scientists understand how solar energy impacts planets directly exposed to it and could provide insight into elemental movement on other celestial bodies. The polar regions of Mercury have captured scientists' attention due to their unusually high reflectivity, likely due to the presence of water ice in permanently shadowed craters. Webb's data also suggests other highly reflective materials may be present, potentially organic molecules brought by cometary impacts. This discovery raises questions about the delivery of organic materials in the inner solar system and their potential influence on planet surfaces in extreme environments. Recent data hints that Mercury may have cooled faster than other terrestrial planets, which is unusual given its iron-rich core. This rapid cooling could be a result of Mercury's smaller size and proximity to the Sun. Webb's observations of surface fractures and deep planetary wrinkles provide evidence supporting this theory. Understanding Mercury's cooling process could offer insights into the thermal evolution of smaller rocky planets, including exoplanets found in tight orbits around their stars. The James Webb Telescope has provided more detailed views of Mercury's mysterious hollows or shallow depressions on its surface. These formations are likely due to volatile elements escaping from the crust. The exact process remains unclear, but these hollows give Mercury a unique appearance among rocky planets. Examining these formations might reveal more about how volatile elements behave under intense solar radiation. Webb's data is also helping scientists reconsider theories about Mercury's origin. New measurements of Mercury's density and elemental composition suggest it may have formed in a different region of the solar system before migrating closer to the Sun. If true, this would make Mercury a migrant planet, which could explain some of its unusual traits, such as its large core and low iron content on the surface. Despite lacking a traditional atmosphere, Mercury exhibits subtle seasonal changes due to its elliptical orbit and axial tilt. The James Webb Telescope's data has shown that these shifts cause changes in the exosphere's composition and density throughout Mercury's year. Observing these seasonal cycles helps scientists understand how a lack of atmosphere doesn't necessarily prevent certain changes on a planet's surface. Mercury's surface is continuously impacted by space dust and small meteoroids, which Webb's data suggests might be gradually darkening its landscape. This space dust impact adds a layer of fine particles, causing subtle darkening over time. This effect, known as space weathering, could reveal more about how similar processes affect the surfaces of airless bodies in space, including the Moon and asteroids. Mercury's large impact basins, such as Calorus Basin, have always fascinated scientists. Webb's images have shown that certain areas within these basins have a strange, hummocky, or uneven terrain. The origins of this rough landscape remain unknown, but it could be related to Mercury's ancient volcanic activity or post-impact geological shifts. Studying these terrains could offer clues about the dynamics of massive impacts on planets. Because of its close orbit, Mercury experiences solar tides, gravitational effects from the Sun that can cause slight shifts in its crust. The James Webb Telescope's high-precision measurements indicate that these tidal forces may contribute to Mercury's surface fracturing and reshaping over time. This finding sheds light on how solar tidal forces influence planetary crusts, a factor that might impact exoplanets orbiting close to their stars. Data from Webb's observations suggest that certain elements, like sodium and potassium, migrate across Mercury's surface due to solar radiation exposure. This phenomenon, known as thermal creep, causes some elements to hop across the planet's surface, eventually depositing in colder areas. Understanding elemental migration on Mercury could offer insight into similar processes on airless bodies and how they affect surface chemistry. Mercury has a faint twilight glow, visible as a soft light just after sunset and before sunrise on the planet. Webb's observations have revealed that this glow is due to the scattering of solar radiation by dust and atoms in Mercury's exosphere. Studying this twilight glow gives scientists a glimpse into how thin atmospheres, or exospheres, can scatter light, providing clues for understanding other celestial bodies with similar properties. Mercury's weak yet persistent magnetic field has intrigued scientists for years. Webb's data on Mercury's core composition and structure might help explain why the planet's magnetic field has lasted so long. This discovery could change the understanding of planetary magnetism, particularly for small planets like Mercury, which theoretically should have lost their magnetic fields billions of years ago. Webb has observed Mercury's responses to solar eruptions, such as solar flares and coronal mass ejections. These powerful events cause temporary but intense changes in Mercury's exosphere and magnetic field. By studying how Mercury's surface and magnetic environment react, scientists gain insights into how extreme solar events might affect other planets closer to stars. The constant bombardment of solar radiation, meteoroid impacts, and surface creep is gradually transforming Mercury's surface over time. Webb's observations suggest that these processes may be reshaping Mercury's landscape at a rate previously underestimated. Understanding this gradual transformation provides insight into the long-term evolution of other rocky bodies exposed to similar conditions. One unique aspect of Mercury is the direct interaction between its surface and thin exosphere. Webb's data indicates that elements from the surface, like magnesium and sodium, are being released into the exosphere due to solar radiation. This exchange process provides a unique look at how surfaces and atmospheres can interact on airless bodies. Finally, Mercury's ability to withstand constant bombardment and solar exposure has offered scientists valuable data on planetary defense. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science, and as sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.